In a recent video lecture, I introduced the topic of clustering, which is basically an unsupervised machine learning technique that allows you to find clusters within your data without actually knowing labels or any classes beforehand. And the first one, the first algorithm we talked about was the k-means. And the idea here is that you iteratively go through by defining random centroids, you iteratively go through and move those centroids around to come up with optimal clusters. And if I write down the algorithm, step one was to initialize random centroids for your clusters. Next, what you do is you find the distance between these centroids and all of your data points, let's say, and all your data points xi. And then you will assign these data points, so assign xi to clusters. And we do that by minimum distance, right? Based on minimum distance between a point and all the centroids you have to find. Next, what you're going to do is you're going to find the average, or you could call that the mean, you could call that the midpoint of each cluster, and that ends up being your new centroids, right? And then basically an addendum to that is going to be, let's say, a 5. Repeat parts 2, 3, and 4 until you have some sort of convergence in your cluster, so they don't really move between these iterations. And I'm missing a very important step 0 here, which is define k. So define k, meaning how many clusters you want. Then you'll initialize k random centroids, and the idea is going to be that you're going to move these k clusters around, these k centroids around, in hope to find the best clusters if they converge at all. And so what could happen is that you might start by defining a cluster here, and let's say I choose k to be 2 and maybe a random cluster here, and they're going to keep moving around. Until, let's say, one cluster ends up over here and the other centroid ends up over here. So you can then say, okay, let's say you can say that these points are part of one cluster and then these points are part of the other cluster, right? Fairly simple. Now, this is sort of a drawback. The defining of the value of k is sort of a drawback because you might not know exactly, well, you don't know exactly how many clusters there should be. And one way of negating that was to do the elbow method, which allows you to basically say that, okay, how about you run this k-means on different values of k. So maybe you start off with, let's say, 2, and you go all the way to 20, and for each of them you're going to be collecting their sum squared errors or the inertia value, and you're going to plot them, and whichever k gives you the lowest inertia, you're going to say, okay, that's the optimal k. Great. But this is also an iterative process, so you're going through this and running it one by one, and you're running k-means one by one, which is itself an iterative process, right? You have to go back and run step 2, 3, and 4 until you reach convergence. So this is a rather lengthy and power-consuming and time-consuming process. So what if there is a different way of doing clustering? There are many ways of doing clustering, but what if there's a way of doing clustering without having to define k at the very beginning? So k will come into play, but not in the way it plays its role in k-means. What you can do is you can say that what if every single point was its own cluster, and whichever 2 clusters are the same, I'm going to combine them into a bigger cluster, and I'm going to keep combining until everything is within a cluster. So I'm sort of building what we call a hierarchy. right? So I'm saying, oh, let's say these two points are, so every point is its own cluster, and then these two clusters are the closest, so they're one cluster here, and then maybe these 2 points are closest, so that's another cluster, that's another cluster, and then that's another cluster, and then you can say that, okay, these 2 clusters are really close, so that's a bigger cluster, and then maybe that's another cluster. So you keep building up until you have one giant cluster. And we'll learn about how to build a dendrogram, using which we can sort of have a split over what is the optimal region where we need to split this hierarchy and say, okay, I split at this point, and however many clusters were below that point, that is the optimal number of clusters I'm going to go ahead with. So you don't have to run k-means several quantity of times, because you don't even know if you found your optimal cluster value at 20. What if the SSE was lowest at, let's say, k equals 22? In that case, you're going to be missing out on that information. But what a hierarchical based clustering will do is it will use a bottom-up approach. So everything will be clustered at the very end, and you'll have much more freedom of specifying when to basically stop and say, okay, now I have found my optimal clusters. So it's called hierarchical clustering. Hierarchical clustering, that's the topic of this lecture. And the way you're going to be doing things is we're going to use a method of hierarchical clustering, which is called the agglomerative clustering. And this basically means bottom-up approach. So every point is its own cluster at the very beginning, and then you keep combining them together to make bigger and bigger clusters until you have one cluster left. So I'm going to write down the algorithm first, because it's going to be really, really easy. And so what you do is you first compute your proximity matrix. Okay, so I'm gonna draw like a very simple data set here. So let's say this was x1. These are my 2 variables that I'm defining things on, and let's say I have a point A here, a point B. I'm gonna give them names for the time being. C, and let's say D is over here, and then E and F are sort of over here. Okay, so I have 6 points in my data set, and I am going to use hierarchical clustering to sort of build up how many clusters and the optimum number of clusters should be in this data set. So I will first compute the proximity matrix. What that means is you're basically going to have a 6x6 matrix here, and every point will be there by itself. So A, B, C, D, E, we'll have one for F, and then you'll have A, B, C, D, E, and then this one for F again. And so basically the diagonals are going to be, you can just call them 0, because the distance between these two, point B and point B, it's always going to be 0. Or you can have infinity. It doesn't really matter. So now what you're going to do is you're going to make a proximity matrix. And proximity matrix basically means how far apart these points are. Now you can use Euclidean distance to calculate the distance value, or you can use the Manhattan and cosine distance. So there are many different ways, again, of finding the distance, basically. But if you come up with one, you apply it for all. And so you're going to basically go ahead and find the distances between these points. So let's say distance between point A and B. Right now, I'm going to just say it's going to be 3, so I'm going to put 3 here too. And then distance between, let's say, point C and D is a good one. So let's say C and D is like 2, right? And then the distance between A and C, it's going to be huge. So let's say that was like a 5. And then you keep building this. You keep building this matrix. And once you do that, now you have computed your entire proximity matrix. So this is the only power heavy consumption basic algorithm here. You're going to be running like a multi-nested for loop, find the distance between every point and every other point. That's going to be the where your algorithm is really, really slow. And then what you're going to do next is you're going to say that let each point be a cluster. So you start off by saying that every point currently, because this is agglomerative, the other one is divisive, where you think that every point is part of one big cluster and you sort of split it out. Instead, you're saying that every point is a cluster by itself. So I have cluster A, B, C, D, E, and F. And then what you do is merge 2 closest clusters. Okay? And then finally, and also update proximity. And you will repeat this step. So this is the only step that repeats. You will repeat this step until one cluster remains. So you have the big cluster over the entire data. One cluster remains. Okay, let's look at step 3 look closely here. And so what I'm going to be doing is, based on these distances, I'm going to combine 2 of my clusters together. Let's go smaller here. And so I know that if I fill this up, even just visually looking at it, C and D are the closest clusters. So I'm going to do this. I'm going to say C and D are now part of one cluster. So this whole thing will become one cluster here. So C comma D becomes one cluster. And once you do that, you're going to update the proximities again. So the distance now, not from A and point C and A and point D, instead the distance now from A and this cluster. Now, this process, this distance calculation, is called linkage. And we're going to be looking at how many different kinds of linkages there are. But for now, just say that I will merge the 2 closest clusters together, which I did. And then I'm saying update the proximity, which I will do. After that, I'm going to then do the same thing all over again. I'm going to say, okay, now which are the 2 closest clusters here? Well, we know that every point itself is a cluster, right? So I'm going to say A and B are closest, so they become one cluster. Okay. And then let's say these 2 are closer than these 2. So then in the next step, I have these 2 clusters become one giant cluster. Finally, E and F become one cluster. And then at the very end, everything basically becomes a huge cluster. And once that happens, then you can stop. All right. So let's actually now interpret how to figure out the optimal value of K here, because we haven't really figured that out yet. And to do that, we will build a dendrogram. And what a dendrogram does, again, is it will basically give you the distance against all of your clusters here. And you will solely, again, use the agglomerative property, and you're going to build up how your clusters were generated. So let's say this was the distance, and we said that at distance 2, I had combined C and D, right? So at distance 2, let's say, I combined C and D here. Let's go red. And they became a cluster. Okay, and then at distance, let's say 5, A and B were closest, so after that. So 5 plus 2, it's going to be 7. So let's say at distance 7, I had let's get it a little closer here. At distance 7, I had A and B become a cluster. Cool. Then I said that these two clusters are going to combine, and let's say at distance like 10, these two combine. So I'm going to then say, okay, these two clusters combine into one at distance 10. Great. Next, let's say at distance 14, E and F sort of became a thing. And so I'm going to go ahead and do this. And then finally, let's say at the distance 20, so for the overall thing, I was able to link everything together. I was able to link them all together, and you had one giant cluster coming out of it. So now, looking at it, you're able to make your own opinion about which cluster you should use, right? So how many clusters you should use. So think of it this way. I could say that, you know, for my data set, the optimal distance between points should be roughly between, let's say, 7 and 10. And so you say, okay, I'm going to make a cutoff at distance 8. And that's great. And so what you'll do is you're going to make a cutoff over here. And then you're going to say whatever is left, so whatever these splits are going to be the number of clusters I have. So I will have one cluster of A and B, one cluster of C and D, a cluster itself of E, and a cluster itself of F. So again, you're basically going to count how many lines, these lines there are. You don't really care for the early splits. Instead, what you're saying is, I've sort of built up a hierarchy. I've sort of built up this hierarchy of my data set, and it is up to me based on the distance, where they should lie. So how many clusters should lie in this data set? Because if I were to split, let's say, if I were to split over here, let's say at 5, maybe, you're going to have 1, 2, 3, 4, 5 clusters. Okay. And then you could say, okay, maybe I want to go up. I want to split at, let's say, 15. And in that case, you're going to have 2 clusters for your data set. And so if you have knowledge beforehand of why these points are far apart, because they are based on your 2 independent variables, so you could say that, you know, this proximity of less than 5 is a good measure. If these 2 points are 5 units apart, then that is me saying that they're very, very different from one another. So in that case, I will then use this as my split and say I have 5 clusters in my data set. So domain knowledge is required when you're doing agglomerative hierarchical clustering, but there is another way. There is another way of doing this, and it's going to be using the health of your hierarchy. And what you want to think about right now is that how long did this hierarchy go between splits, basically? So what I mean by that is you will find the distance range within the biggest, so the biggest distance range within which there were no new splits. So the health basically is talking about how long did you spend, how much time did you spend not actually splitting. And so in that case, you will find the biggest distance range within which there were no new splits. So what I mean is, so let's say between distance 0 and 2 here, between these 2 points, these two areas. So let me draw a line over here and one over here. You'll notice that you split once, right? Okay. What if we go back a little bit and we say, okay, what if between let's say points 3 and 4, so points 3 here and 0.4 here, and so I'm going to make this line. You're going to say, okay, no splits happened, right? That's good. But is this the biggest range within which no splits were happening? So right now you can already see that here is a place where no splits happened, but the biggest one is actually over here, right? So this area, this location, let's say between 12 and 18 for now, this location, this range had 0 new splits, and it was the biggest range compared to every other ranges where there were no splits. So you have, let's say, one over here, like, right? So no splits happening over here. You have a one over here, and then one over there. So I'm making this very confusing here, but this is the biggest range of your distance value within which there were no splits. So this is where you're going to be intuitively thinking that, okay, at this point, so let me put them A and B. At this point, what should have happened, theoretically, is that you should have built up all the small clusters in your data that needed to be built. And here, around this point where you have the biggest range, where no splits were happening, you're getting closer and closer to finding your final big 1 or 2 clusters. So this is a very good area of finding your optimal value of k. So what you do is you say, okay, I'm going to choose my k within this set. So I'm going to split my dendrogram. I'm going to prune everything. So what basically means is that I'm going to remove any further splits that I made beyond this area. And what I am left with are 2 different clusters. I am left with this cluster and that cluster. So I'm left with a cluster that looks like this and a cluster that looks like that. So if I were to redraw this, if I were to remake that data set here, let's see how good I can just copy this. So I have points A, B, C, and D, and then E and F here. So based on this, based on using the health, I am able to then say that I have 2 clusters. One of them is here, and the other one is going to be here. Now, you might be thinking that this is still me picking out a k value, right? I still had to go in and say, you know, I'm going to split on that. But you'll notice that I actually never went and said, I'm going to pick this split point because it had 5 clusters, or 4 clusters, or 3 clusters. Instead, I'm instinctively using the data itself. I'm only using the distances between these points or these clusters to find a spot to split my dendrogram on. So I haven't actually picked the k value. It was picked for me from this algorithm. And that's pretty awesome compared to k-means, where you started off saying that, you know, I'm going to pick a k value and I'm going to stick with it. Let's say you use the Agglomerative method and everything like that. But here, you could have picked, let's say, a split of this point, where in that case, you'll have 1, 2, 3, 4 different clusters. Or you could have picked this point, where you have all points as separate clusters. But never did you actually pick a split point based on how many clusters it made. You picked it based on the distance or the health of the hierarchy. So I personally think that hierarchical clustering is a better clustering algorithm compared to k-means if you don't know the value of k optimally. So think of it this way. If I give you a data set, and it has, again, it's 2-dimensional, and it looks like this. You draw a diagram, you draw this scatter plot, and you look at this and you say, well, intuitively speaking, there should be 1, 2, 3 clusters. And you will be right. You will be very right. And it shouldn't take long to compute this. But if I give you this data set, let's say I give you points like this, in that case, you're going to have a hard time figuring out how many clusters there are just looking at this diagram, right? You could say this whole thing is one cluster, but what if they were basically just clumped together? And the distances between these points really do matter. In that case, you're going to use I'm going to say that hierarchical clustering is going to be a little bit slower than k-means, but you're going to use k-mean, you're going to use hierarchical clustering to build up a dendrogram. And then so you're going to, let's say, make a hypothetical dendrogram here. And let's say this is your hypothetical dendrogram, and these are all your points, D, E, F, G, H. And then based on wherever you saw the biggest range where there were no splits, let's say over here, based on that, you're going to say, okay, I have 1, 2, 3, 4 different clusters in my data set. So A and B are going to be one cluster, A and B are separate clusters, C, D, E, F become one giant cluster, and then G and H become one cluster. So definitely think about what kind of data you have, and based on that, you should be able to make an intelligent choice between k-means and hierarchical clustering using the agglomerative linkage method. So let's take a little time and talk about all the linkage criterias that there are. And linkage basically means finding how close or how far clusters are from each other. And there are 4 different kinds here. The first one is called single linkage. You can also think of it as the minimum linkage. Fairly simple idea. And the idea here is that if you have 2 clusters, let's say A and B, these are 2 clusters, A and B, and they have points like this. What you're going to be doing is you're going to find the distance between the closest points of those 2 clusters. So what you can say is that this point and this point from these 2 clusters are the closest, right? So your distance, your overall distance between the clusters is going to be based on this guy, whichever the distance between these 2 points is. And so the algorithm or the formula, fairly simple. It will be that the linkage between clusters A and B is based on the minimum distance, so this is the distance function, between, let's say, xai and xbi, where xi and bi are the points for each cluster. So what you're going to be doing, technically, is you're going to find the distance between all of these points, right? But you're only going to be using the distance afterwards, which is the closest. So the single linkage, meaning the minimum distance between these 2. And intuitively, there should be something in the opposite. So the second one is called a complete linkage, or max linkage here. And so the formula just changes where you go. AB is going to be the max of the distance between xai and xbi. Okay, so by that I mean, again, let's say you found, let's go black. Let's say you found the distance between this point and these points and this point and this point. You're going to do the same for all points here. And finally, these 4. Okay, so you're going to find the distance between every single point and every other point. And then you're going to say, what was the minimum distance? If the minimum distance was between these 2 points here, if this distance was the minimum, then you're going to say that if you're going to use single linkage, you're only going to look at the minimum distance across all of these distances. And then whatever the minimum distance was, you're going to say that is the value I'm going to put in my proximity matrix. With complete linkage, you're saying, give me the maximum distance. So the points that are farthest in the two, let's say these 2 points, or actually it should be these 2 points. So the points that are farthest from each other, whatever their distance was, that's the value I'm going to put in my proximity matrix. The next one, let's do this. The next one is called average linkage. And in average linkage, what you're doing is you've already computed, you're going to always compute all the distances. What you do is basically find the average of the distances. So by that, I mean that your linkage formula should be the average. So the number of points of cluster A, number of points of cluster B, and I goes to, so for all the points in first cluster and for all the points in the second cluster, I am going to find the distance between xai and xbj, right? Okay. In this case, what you're again doing is not relying on just a single distance. You're going to find all the distances and make the average. Find the average, and that average distance value is what you put in your proximity matrix. The fourth one is called Ward's linkage. And it's to do with centroids, basically. So what you instead do, instead of finding all these distances, what you do is you find the centroid based on each cluster. So centroid here, centroid here. So again, the centroid is going to be computed by the midpoint of all these points and the midpoint of all those points, and you're going to find the distance between those midpoints. So it's sort of like average linkage, but instead you're finding the distances within and then looking at the distance here. And whatever the distance is, you're going to put that as your in your proximity matrix. But again, the idea is that you're going to, so think of it this way. Your pre-processing steps should be something on the lines of picking your distance function. So Minkowski, Manhattan, cosine, Euclidean, whatever you choose, you will have to pick one. And then picking your linkage criteria. So again, based on sort of your data and the pros and cons of each of these, you're going to also specify which linkage criteria you're going to be using. This image is very often used when describing how the different linkage mechanisms are going to be working. So with a single linkage, when you're only looking at the closest point, so the closest distance, so the min distance value, for spherical data like this, it works great. Average, complete, and Ward don't really work that well here. Same idea for a very oddly shaped data set again. Single linkage works best, but then you'll notice that single linkage basically works best when your data is oddly shaped, because now this might be what you're getting. So in this data, what you're seeing is there are two dense regions. So these two are dense regions, and then you sort of have this scatter of points happening. Single linkage, because you're looking so concretely between points here, if there is sort of a noise aspect happening, it is not going to do well. Instead, you can look at average linkage, which still was able to find 3 clusters, complete linkage, or Ward linkage, where again, once you have found your clusters and everything, you're basically your clusters, you're looking at the distance between the centroids. And in that case, you were very easily able to sort of extract 3 really good looking clusters here. Single linkage again does not really work well here. In this case, average linkage only found 2 clusters, complete linkage only found 3, and word linkage almost got to the right answer. Note here that if your data points are really scattered and dense within their own cluster sets, then you're never going to have any issue with either of these linkage methods. But in this region, this is a really good plot, where everything is uniformly distributed, so there's currently no way of finding if there should be any clusters here. You'll notice that single linkage even still finds 3 clusters, so there's 1 point for the orange cluster and a couple of greens, but everything else is blue. Well, with average linkage, complete, and ward, it still is able to say that there should be some sort of divide happening across all 3. So based on your data, based on what your data looks like, you could use this as a reference point and see which linkage criteria you should be using for your data sets. Another really cool clustering algorithm is called dbScan. dbScan, and it stands for, this is a big one, density based spatial clustering with an application to noise. So clustering algorithms are very much useful when you're looking at spatial features. So let's say let's say this is my longitude and this is my latitude value, and we sort of have these set of points here. And what you're trying to do is sort of figure out if they're compact together, they should be put into a single cluster or not. The cool thing about dbScan is that it doesn't really compute any k for you. Instead, what it'll do is it'll ask you how many points, so number of points there should be in each cluster, and what is the radius of each cluster. So it's assuming that they're almost spherical, so radius of each cluster. So based on these 2 parameters, these are your parameters that you're going to pass to this function, this algorithm. Based on these parameters, it will find as many clusters that it can that sort of fit this criteria. And when I say application to noise, the cool thing it does is that dbScan will, let's say, tell you that these points are clusters, 1 single cluster. And then these points are cluster based on, again, these criteria. And then let's say these points are a cluster, right? All of these. What it will do, in fact, the application to noise part, it will actually find points that it thinks should not be part of any cluster. So it's saying that these are noise values. These over here are noise values. So not only does it find the optimal number of clusters based on some criteria, it will also find points that it thinks shouldn't be part of any cluster. This is something that k-means or hierarchical clustering, agglomerative clustering don't actually do. And what else you can do is, I can make this, so let's do it in yellow. I can make this HDBScan. So that's another algorithm where H basically means hierarchical. The hierarchical density-based spatial clustering with an application to noise. And in this case, when I do hierarchical clustering, I don't really need the radius of each cluster. I just need the number of points, and it will do the exact same thing basically that the agglomerative clustering does. So it will still go ahead and build a dendrogram of all of your points, let's say like this, And then it will also look at the health, so the largest distance range within which there were no splits, and sort of split based on that. But it will also have this noise application to it. So these two are a lot more complex in what they do and how they're working, but the idea basically still came from these very naive little, algorithms like k-means and agglomerative clustering. So as a closing note, we have now looked at several clustering algorithms, and they're all unsupervised machine learning techniques. And again, the idea is that you don't really know how many clusters or where the clusters lie in your data, and you're hoping that using this unsupervised technique, you're able to find them all. Each of these clustering algorithms are basically using different criterias, but the idea again is the same, that you're looking at the distances between points to sort of find out how close or how far they are and whether or not they should be part of a cluster.